There are two types of physical changes that involve enthalpy changes, the first being changing states. This involves breaking the intermolecular forces, which is endothermic, between particles when you're taking a compound from being solid to liquid to gas, or forming intermolecular forces, which is an exothermic change if you're going in the opposite direction. The graph below is known as a heating curve, where you take any substance and add heat. If it starts off as a solid, and if you add heat, the temperature will slowly rise until you get to the substance's melting point. Then we notice that the temperature stays constant until all of the substance has melted and turned into a liquid. The heat that is added during this stable temperature is known as the delta H of melting. This heat is used to break the intermolecular forces holding the solid together. Once those intermolecular forces are broken, the heat that's added will go and increase the temperature of the liquid again, until the same thing occurs once the substance has hit its boiling point. The energy required to change a liquid into a gas to break those final intermolecular forces is called the delta H of vaporization. Opposite state changes have the same energy values, but their signs are flipped due to the energy direction. So if you're freezing something, it's just the negative value of the enthalpy change of melting. If you're condensing a gas into a liquid, it's the same energy value, just flip the sign for the delta H of vaporization. Now here's a specific example. If we melt ice, since hydrogen bonds need to be broken to change water from a solid to a liquid, this process is exothermic. The system will absorb 6.02 kilojoules of energy from the surroundings for every mole of water, which is why, in order to melt ice, it has to absorb heat. The second type of physical change that involves an enthalpy change is dissolving a solute into a solvent. Depending on the type and number of intermolecular forces involved, dissolving can either be endothermic or exothermic. Here's an example. If we dissolve hydrochloric acid in water, the delta H of solution is minus 74.8, which means whenever you dissolve hydrochloric acid in water, the surroundings heat up. In a nuclear reaction, an element transforms into one or more different elements. When new nuclei are created, the number of attractions between protons and neutrons in the nucleus change. These are called strong nuclear forces. Forming more of these attractions releases huge amounts of energy. This energy is made from converting some of the mass of the protons and neutrons into pure energy. For example, if we make 1 mole of carbon from its components, if we take 6 moles of hydrogen and 6 moles of neutrons, that gives us a mass of 12.098940 grams. Remember, a hydrogen is 1 proton and 1 electron, so that would give us an atom with 6 protons, 6 neutrons, and 6 electrons, which would match the components of a carbon atom. But we find the mass of 1 mole of carbon is 12 grams exactly. So we have a missing mass of 0.098940 grams per mole of carbon that's made. That might seem such a small, insignificant mass, but we can use Einstein's equation E equals mc squared to calculate how much pure energy is in that missing mass. When we do that, we get 8.9 times 10 to the 9 kilojoules per mole of energy released. Comparing that to a 400 to 4,000 kilojoules of energy released from forming an ionic crystal, making a mole of carbon from its components releases huge amounts of enthalpy. There are two different types of nuclear reactions. The first is known as nuclear fission. It's when a heavy nucleus splits into lighter nuclei, resulting in a vast amount of energy released. An example of a nuclear fission reaction is the one we use to produce electricity in nuclear reactors. It has an enthalpy change of 2.1 times 10 to the 10 kilojoules per mole of uranium. Watch the animation to see how this reaction works. In a very simplistic explanation, we take a uranium-235 atom and shoot a neutron at it from a gun. It splits into two smaller elements, krypton and barium, and produces more neutrons that can go and fly around and hit other uranium atoms. Another reaction that happens with uranium-235 is it can be split into a rubidium and a cesium, but it also produces two neutrons that can continue the chain reaction. The other type of nuclear reaction is known as fusion. It's when two smaller nuclei join to form a larger nucleus. An example of nuclear fusion is a reaction that occurs in the Sun, where we take a hydrogen 2 atom and a hydrogen 3 isotope, and they get squished together through the intense pressure and gravity of the Sun to make a helium and a neutron. This reaction has an enthalpy change of 1.7 times 10 to the 9 kilojoules per mole of helium. There's a neat little chart on page 231 showing a comparison of different energetic events and what the enthalpy change is. Check it out.